So, before I start talking about the Coccolithophores, I would like to say that it is a real pleasure to work with them. First of all, because of their beauty. It's very attractive. It's a pleasure. But deeper than that, for their complexity, which can be unraveled. And for, I would say, their creativity. It's a group absolutely fascinating to study. And I would encourage any student who loves nature to come and explore them. There is still so much to do. So, what have we done this week? We have talked a lot about the Coccolithophores, but there is one question which has not been addressed, which is, what is the adaptive roles of the Coccoliths? As Jeremy was saying, they probably expend a lot of effort, energy in making the Coccoliths, and yet we do not know why they should do so. And as Amos has indicated, it's also very important for the budget of the ocean to know whether they are really autotrophic or not. So my question here would be to try to understand the adaptive role of the Coccoliths and wonder what is the relationship between coccolith morphology and ecology. There has been different raisons d'être for the Coccoliths, and different proposition has been made. I have to turn one thing here, sorry. So it has been, they have been explained as physical protection, in particular protecting the cell from viral infection or from grazing. Have it considered a physiological role like collectors or uptake of nutrients. And I have proposed a different thing, which is interaction within the community, with mixotrophy, and perhaps, and you have some time to think big in paleontology, perhaps bacterial farming and food capture. So today, the preferred interpretation, the preferred role given to them is grazing as the forcing mechanism which has forced the development of the Coccolithophore evolution in the Triassic. And together, perhaps with them, photo damage and viral infection as secondary effects. I would like to bring here a different perspective. All what has been done here is look at the Coccolithophore in the modern ocean. But we can wonder whether we can learn from the fossil record. Do the Coccolithophore, as they evolve, tell us something about the role of the Coccolithophore? And my group of choice is here, the Discoasteral here, which I have chosen here, because this is a group with an abundant fossil record. It's over 50% of the assemblage at low latitude. It has a large longevity, more than 60 million evolutionary span only through the Cenozoic. They were already present in the Mesozoic. They have a large diversity in the Cenozoic, 16 genera, 500 species. I'm talking of paleontological species, probably many, many more species. And the interesting thing about them is they occur in warm oligotrophic waters. And moreover, the macroevolution is well understood thanks to the work, preliminary work of Prince and Romain. So it's also interesting because we always in the literature consider that these Coccoliths are heavily calcified morphology. And you see here Coccoliths, which actually look very robust when you want to compare them with Coccolithophores of today. So what is my methodology? Well, I tell you, at home, it's like kindergarten every day. In the sense that what I do is look at Coccoliths and try to interpret their structure, how they are made. So we have here Coccoliths taken from the literature, because in the literature you find a lot of Coccoliths, some well preserved, very few actually, many very poorly preserved, and intermediate level of preservation. And when I find a very interesting Coccolith like this one, then I try to understand its structure, like here. The figure you will see are color-coded. A coccolith is sitting on a spherical cell, and as a result, one side of the coccolith will be concave, the one which rests on the cell, and the other one will be convex, the one away from the cell and which is bathed in the water. And I give them names just for simplicity. So it's nice to have a terminology that allows us to convey information. Then when I have done that, then I try to figure out which are the homologous cycles. This was the ancestor of the group. It evolved very, very shortly after the KP boundary. And again, everything is color-coded. This is the proximal part, the one which rests on the cell. And I think you can see here, between very different morphology, as seen here, a large resemblance. And this is the distal face, and you can see the structure here is very much reminiscent of this one. This is a form which is very derived, and as a result, the shape is quite different. What is really fascinating about the discoesteral is that the way that they make the cycles of elements, as Jeremy has explained, the elements that form such coccoliths are organized in cycles, as you can see here. And in most cases, the cycles are arranged in concentric fashion, as you can see here, or as you can see here. But the discoesteral have done something else. They have put the cycle in superposition, and you see here. And this has allowed for a tremendous diversification. So, if we put together the fact that the coccoliths of the discoesteral are heterococcoliths, meaning they are made of cycles, and the ancestor had made a coccosphere which is actually, you will agree with me, relatively similar to a coccosphere of Calcidiscus. I think it is very reasonable to say that the discoesteral are Coccolithophores. So I have been, as I said, drawing a lot of coccoliths from the discoesteral, and this is the diversity that you see. I have paid a lot of attention to the detail, which is the texture of their surfaces. And to obtain something like this, or this reconstruction, or actually description, I have to go through a huge database, which is going to be available online at SCPN very soon. But among the form which I've been looking at, probably less than 5% have allowed me to do this type of work. And from this, I have concluded that coccoliths are actually lightweight construction. They are strong, but they are also delicate. And when we look at this and we think of them as being on a cocosphere, then we have to say that coccoliths are not protecting the cocosphere. Coccolithophores, in other words, are not armored. So what we see most often in oceanic sediments is this. The discoesteral coccophores have a tendency to recrystallize very easily, but this is what they look like originally, like this or like that. And if it's a discoesteral and asterolith, then this is what they may look like today, but this is what they looked like in the past. And now the little dump holes here at the lower side, on the concave side, the proximal side of the coccolith. So once I have done my reconstruction of the coccolith, then, or my description of the coccolith rather, then I proceed with the reconstruction, very tentative reconstruction of the coccosphere. But we know that the ancestor Biontolythus was making a coccosphere. So the other genera, the other species, had to make coccospheres again. There is a problem here, or a limitation here, is that I have no idea of the size of the cell. But I can figure out there were not too many coccoliths during the Paleogene on these coccospheres, because when we compile the number of coccoliths on fossilized coccosphere from the Paleogene, the number is really above 20. So I have taken this as a model. So again, the cell here does not come into account the size of the cell. What I am interested, you see a lot of texture on this coccolith, and this is what I am interested in. So what I show you is through the Paleogene, Paleocene and Eocene. This is the KP boundary, the Paleocene-Eocene boundary, the Eocene-Oligocene boundary. And this purple line shows a range of these different taxa, genera in the discourse asteral, and the thickness of this line show you the diversity, how many morphotypes in the group. So you see a vast diversity, and there is a lot of information in something like this. But what I want to do, what I invite you to do, is to look at this with me, which is the evolution from Lithopticus, this form which are like a little drum, if you like, which have little fluted drums here, two drums here which have an alveolar pattern, the genera Coccolithopticus and fasciculiths. And we project the first occurrence and the lifespan on this particular curve here, which is delta C13 curve, which has been made in 2000, published by Kramer et al., and which is a revision of what Zakos and others have published in 2005, but at greater resolution. And we see through this time here an increase in the delta C13 in the ocean, which is very poorly understood, which results from high accumulation of organic matter at the bottom of the ocean, probably due to high productivity, and also with oligotrophication of the ocean. The planktonic foraminifera are here, just below this boundary, just before Lithopticus evolved, are indicative of change towards oligotrophication in the ocean. So let's look at these coccoliths here. So it's a little simplified here, Lithopticus, fasciculiths, these fluted coccoliths, and you see at the surface they have these notches, if you like, and those in contrast have the notches, but also they have a lot of fenestra. They have an alveolar structure. And for this reason, I call them honeycombed fasciculiths and here fluted fasciculiths. So what is the difference? When if you look at cross-section, well, this here, in cross-section, you will not see very much structure. You have to go to the side here to see the structure, to the lateral view. But you make a cross-section here, and then you are going to see an alveolar pattern, which is extremely developed. So what does this mean? How do we interpret this? So we have to think about a cell in the water and how a cell gets its nutrients. The nutrients are absorbed by the cell through diffusion. And there is for every cell in a particular environment an ideal surface to volume ratio for the cell to acquire exactly the amount of nutrients that it needs to live properly, to metabolize, to divide, and so on. Now there is a problem because there is an arrangement here which is good and which is not good for the cell, in the sense that most of the cell of Coccolithophores are spheres. And the spheres are those geometric forms which have the smallest surface volume ratio. But this means that when the cell grows, the volume to surface, or surface to volume ratio is not linear because the volume is cubed while the surface is squared. And so if the cell size has to increase, then the volume size has to increase, then the surface must increase as well. So how do we increase the surface? Well, a good way to increase the surface is to make coccoliths. And this is how I interpret this, the change from fluted shapes in the fasciculiths at a time when oligotrophy in the ocean is still little, to this pattern when oligotrophication is much more pronounced. So how does it work? We've made something very simple that will have to be refined, in particular we will have to measure this different surface here. But if you have a coccolith of this type here, which has no structure at the surface, and you consider a cylinder 10 micron in in diameter, then the surface volume ratio is 0.4. Now, if you start to make the fluted pattern, as we see in this coccolith, then the SV ratio is 0.72, which is enormous, almost double. And if you start making this alveolar pattern with this fenestre, then it is 0.87. So what it means, I think it's clear, that coccoliths are integral to the physiology of the cells. And I would say that they are support for mixotrophic physiology. In other words, the true coccolithophore, by this I mean not the Brachydophyra and not the Isocritidon. Sorry for that. But what I see as the true coccolithophore, they are mixotrophic they have a mixotrophic physiology for many of them, and the coccoliths are part to their physiology, very much like I would say, like our bones. Our bones are necessary to us in more than just giving us a skeleton, and I think the coccoliths do the same for the coccolithophore. So let's ask ourselves, how realistic is this interpretation? First of all, how common are symbiotic relationships among planktonic species today? Well, planktonic foraminifera, it's well known. There are many of them, those who live in the upper part of the ocean. They are the dinoflagellates. Diatoms, well, Amos yesterday showed symbiosis between diatoms and coccolithophore. And Brachydophyra bigelow is giving us a good example of symbiosis with bacteria. So we can ask ourselves, are there similar textures in the coccolithophore today? And how do coccoliths from species who live in oligotrophic waters today look? So here is the living species, Calcidiscus quadriperforatus. At the diploid phase, this is how it looks like, very relatively robust against stiff coccoliths. This is how it looks at the haploid phase. And at the haploid phase is known for living in very oligotrophic waters, unlike the diploid phase. And what we see is a very porous texture, a lot of fenestre. This is very reminiscent of what I just described in the fasciculiths. And if we look at a diversity of holococcolithophores today in the ocean, this is from a book which I am completing at this time, where I have described every one of these holococcoliths are good to try to understand their structure. We see also that many are very porous, have large windows, are very amenable to possibly mixotrophy with bacteria in the ocean. Look at this, look at that. The shapes themselves plus the structure, it's just so beautiful. So what about now in the photic zone today? Who lives there? So I've taken two examples. One is a trumpet shaped of Discospheres tubifera, and the other one is Ambelosphera tenuis with this pyrotheca, in which the coccoliths inside the cell are much smaller, and then larger coccoliths surround the whole coccosphere as if enveloping everything. It is easy to imagine here that in all this space there is large place here for mixotrophic relationship, where the cell may be delivering a lot of metabolic products and bacteria come to live from that. And it is also easy to imagine interaction here between bacteria and coccolithophore. Now, if we look in the deep zone, then here is Florisphera profunda. Very different, right? It has numerous coccoliths, it needs amphiballast, and they have smooth surface. And I would venture to suggest that instead of being mixotrophic, Florisphera profunda is mostly heterotrophic. So here is my idea of the photic zone. This is my garden in the photic zone. So this is Discospheres tubifera with the coccosphere. We have the inner coccosphere here, which is the base of this coccolith, which form kind of continuous envelope, and then all these trumpet shaped things from which a lot of metabolic products may be coming, or maybe a lot of water loaded with nutrients can go into the cell. Now, what is most missing for a cell living in oligotrophic water? It's nitrogen. So how can it capture? How can it get the nitrogen? It cannot itself use the nitrogen from the atmosphere, but it can establish a relationship with the diazotrophic bacteria, those with fixated nitrogen. And if it does that, these little bacteria come to eat the metabolic products from the Coccolithophore, at the same time fixing the nitrogen and providing the Coccolithophore with it. And there would be many other bacteria environment. Here I have represented some cyanobacteria as well. So my view of the photic zone is that of a garden in which the Coccolithophore establish strong relationship, in this case, with bacteria to obtain the nutrients that we need. And the bacteria in turn get nutrients, which are the metabolic products from the cells. So with this in mind, let's think of how a late Paleocene photic zone would have looked like. So this is my gardens of dreams. This is fasciculiths in cross-section. It's a cross-section of the cell and a cross-section of the coccolith. I have showed you before all these alveoles in the coccolith. I have made a bubble here because just like in the living, I think that would be some sort of mucus around the cell with the metabolic products inside and also the nutrients coming, some brought just diffusing from the water, and many others like the nitrogen brought by the bacteria. And so here is my reconstruction of a late Paleocene oceanic garden. Before I end this talk, I would like to ask you biologists, if you are listening to me or to us during the week, I would like you to remember that the Coccolithophore have a long history, and that today we are studying crown taxa, and that probably if we look at, as I show here, if we look closer at the paleontologic record, or if you look with us at the paleontologic record closer, we would probably be able to answer even more questions that the paleontologist alone can. And for us fellow paleontologists, I would like to say that behind every single coccolith, which is just like an isolated sedimentary particle, behind every one of them, there is a living organism. And therefore, every single coccolith obeys to the rules of biology, and in particular, with regard to morphologic variability. So whatever we are doing, paleoecology, paleoenvironmental studies, biostratigraphy, we have to remember that we are looking at a remain of a living organism. So with this, I thank you for your attention. And I would like to express my deepest thanks to Felipe, Daniel, and Alejandro. They have brought us together around NannoTalks in this very difficult time. And it has been a pleasure to hear all these talks during the week. But this would not have been possible for the vision of our three colleagues here. And I would like to thank them very deeply. Thank you.